Good afternoon, everybody. I hope you guys are having an awesome day. And today we are going to continue our discussion in chapter 14. And today we're going to talk about vapor pressure and boiling point. Now, I know I did a demonstration yesterday, hopefully, on boiling and evaporation. And we're going to continue that a little bit today. And today we're going to talk about the difference between vaporization or evaporation. And when we see this, I know that we're probably always just thinking of the gas form, and they both are a conversion of a liquid to a gas. And we know that it's going to require energy to do that. If I could get you to imagine again, like I'm always asking you to be the molecule, be a liquid, you're kind of floating around, hanging out with your friends inside of that beaker, you have to gain some energy, create some more collisions going on inside of that container in order to gain enough energy to become a gas. Now, if we look at evaporation, we can see that it's going to happen in an open container. It's going to happen at the surface. It's a really important piece over here that it's going to happen at the surface. And so, yes, it can be accelerated by changes in temperature, but we can't stop it from happening. And so it happens at the surface at a range of temperatures. And if we were to put a beaker of water in this room, yes, it's going to evaporate. We can't stop that. However, we could speed it up or slow it down depending upon the temperature in the room. Particles have to have enough kinetic energy, and remember, kinetic energy is the energy of movement, to overcome some attractive forces. So if you can think about these molecules down here in the solution, they have some attraction between each other, and they have to have enough movement to break that force that's there in order to gain enough energy to leave the liquid. Of course, they're going to speed up when they're heated, and the more energy that we have there, the more molecules that are going to escape. So then, I know that some of you are in some athletics, or maybe you like to work out or go hiking or ride a bike. We know that sweating, you've been told since you've been really little, is a cooling process. And it actually is. If you think about it, your sweat, when you sweat, particles that have really high kinetic energy are trying to escape and cool your body down. And it says for the next statement, the average kinetic energy of the remaining particles is lowered. Well, if that's being lowered, then you are cooling your body down, and that's what perspiration actually is. Your body is responding to that workout that you are putting it through. All that energy that you are building up in your body, it needs to release, and that is in the form of perspiration. All right, so evaporation then, if in a closed container. As the particles vaporize, they collide with the walls and create what's called vapor pressure. And I think we talked a lot about that in the last chapter. As a way to generate pressure is the molecules are continuously hitting each other. They're colliding with each other and they're colliding with the walls. And some particles are going to go from a liquid phase, as you can see here, into a vapor phase. And then you're going to have some go from a vapor phase into a liquid. So I know some of you probably have a water bottle sitting in front of you that you have opened, and it is now closed. You have this cap on top of it. And what's going to happen is right now, at the room temperature that it's at, some of the molecules are gaining enough kinetic energy and they're leaving the medium that they're in. They're leaving the water. And then they're forming water droplets. Now, if we sit and let that water bottle that you have in front of you sit for many days, you're going to see some condensation. You're going to see some water droplets forming on the inside. Now, what that is called is that's called equilibrium. Now, a lot of times people feel that when they hear the word equilibrium, that it's equal and nothing else is happening. But what's really going on here is a lot of craziness. There's all sorts of things going from a liquid to a gas, from a gas to a liquid, back and forth, back and forth. And that's what you see in this drawing over here, that this is at equilibrium. We have just as many molecules going into the gaseous phase that are losing energy and going back into the liquid phase. Over here, we have more going in this direction, and so it hasn't reached equilibrium yet. So we can get to a point where the rate of evaporation equals the rate of condensation. Now think about that for a moment. Like, that's a lot going on, and that would be this over here, this container, your water bottle, after several days. Now, we talked about that vapor pressure, that pressure that is generated inside the water bottle. So vapor pressure increases with temperature, as you probably would think, and you can see this with this chart over here. If I redraw this line, you can see that as my temperature is increasing, the vapor pressure is also increasing. So that means more particles are escaping the liquid and they're becoming into the gaseous phase. Now, I hope you might be thinking, do all liquids do this? Yes. Do they all do it at the same rate? Excuse me, at the same rate? And the answer would be no. So yes, different liquids have different vapor pressures. Now, I know this is pretty small on your chart. It might be hard to read. It is for my old eyes up here. But we can see that we have water over here on the left, and we have carbon chloride, methanol actually, over there on that side. And so if we look at that, how this chart says is that at the highest temperature, this has the lowest, actually, vapor pressure. So this is the lowest vapor pressure, and this is going to be the highest, is how we call it. So what that means is that if it has the lowest vapor pressure, going from a liquid to a gas takes longer. So this is going to take longer. It's going to require more energy. And this is going to happen much faster over here. Now, I know things that you have had common contact with is like fingernail polish remover or gasoline or paint thinner. Those things evaporate very, very quickly because they have the highest vapor pressure, very high. You could have some water droplets of some spilled water on your counter, and it's going to take a long time for that to evaporate because it has very low vapor pressure. Now, we can have look up values of vapor pressure of all these different substances, and they used to be measured with a manometer. Now, we have much fancier devices now, but a manometer is something that mercury, we know, responds very easily to a difference in temperature change. So if you can imagine that you have some liquid down here, yes, evaporation is going to happen. It's going to create some vapor pressure. So we're going to have some particles that are up here, and that's going to create more pressure, and it's going to go through here, and then you are going to see that it's going to press down on this mercury. Well, if this is open up here to our atmosphere, it will be whether the pressure here is greater or less than the pressure that's being felt on the outside. And the difference in these values is a calculation that you can do in calculating vapor pressure. And so if I were to put water in here and I were to put methanol or carbon tetrachloride in here, they would have a different difference over here, and that means they have different values for vapor pressure. And when you think of vapor pressure, just think about how quickly things can evaporate, and that will give you an idea if it's high or low, something just to keep in mind. Okay, so this is just a short little lesson here. I hope you're having a wonderful day. Keep working on those book questions, and chapter 14 is very short, so you don't have time to fall behind. You guys have an awesome day. Keep being positive protons, and I'll see you soon.